So to start this next segment, we are going to look at heating curves. So heating curve, we're starting at a low temperature and we are warming up a solid up through its phases into the gas phase. In our last lab of the semester, we're going to look at cooling curves. So we're going to look at starting, say, at a higher temperature and working our way down. So this would just be a mirror image or sort of like this in that last lab. Okay, but for us, we're looking at heating. And this looks kind of odd. So we're looking at added heat here. So as we go from low temperature to high temperature, we have to add in heat energy. But there are some places, like orange here and this pink, where we're adding in energy or heat, but we're not getting an increase in temperature. So what's happening here is you probably can guess if this is water. Here, we'll label that. So if this substance is water, let's look at where this first horizontal segment is happening. It's happening at 0. And so hopefully in your mind, you're thinking like, I know what temperature that means for water. But let's look at the second one. That one's happening at 100. So hopefully you've put together that the horizontal, these are happening at phase changes for water. So this here, we have the solid going to liquid, and here we have the liquid going to gas. So those are happening at phase change. So what's happening during a phase change is we are adding in energy. You see that we are still moving along the x-axis here, but it doesn't result in a temperature change. So at a phase change, what we can say is all added energy goes to breaking intermolecular forces. Okay, so all of the energy added into the sample is going to break those forces. Okay, so depending on the substance, like for example here we have water. This one's kind of large. We'll see this one's also, kind of large here. There's a lot of strong forces holding water together. So these flat regions are quite large. In fact, this here goes from, this one lasts for about 40 kilojoules. Okay, so 40 kilojoules to take our sample of water to go from the liquid phase to the gas phase. Down here, this one only takes about 6 to go from solid to liquid. But again, so we don't see temperature changing because all of the energy is going into breaking those forces either. Okay, so we see these ones here are in the solid phase, liquid, and gas. For those ones in solid, liquid, and gas, energy is going to the kinetic energy of the water. Or again, if this is ethanol or methane, whatever it happens to be, all added energy is going to increase the kinetic energy of the sample. So that's why we see temperature going up with added energy. The molecules are moving faster and we are getting more energy into the sample. Okay, so we can measure the energy required in each of these steps here. So a couple of these will be familiar, hopefully. So this blue one, we can use Q equals M times C times delta T. So we can use our standard heat formula here, where that C is the specific heat of the solid. So specific heat does change as we move through the phases, and we'll see that when we do our example with water. So we can use Q equals MC delta T here. Okay, so for this segment, Q is equal to N delta H of fusion. Okay, N delta H of fusion. So the number of moles you have, N, times the enthalpy of fusion, which is given in units of kilojoules per mole. So number of moles times our delta H. Okay, so again, when our temperature is increasing, we go back, we can use Q equals M times C times delta T, where now our C is going to be the constant for the liquid phase. Up here, same thing, so it's sort of the flat region. Q equals N delta H of vaporization. So N delta H vap. And then finally, our last segment, Q equals M times C times delta T, where this C, again, all of these C's a little bit different. That would be the C for the gas. Okay, so let's say we wanted to calculate the energy required to take a sample of water from negative 25 degrees Celsius to 125 degrees Celsius. So we want to go Q of water going from negative 25 degrees Celsius all the way to 125 degrees Celsius. Okay, so we'll definitely get to do each segment. So we're going to have to do 1, 2, 3, 4, 5 separate steps. And then we're going to sum the energy together at the end. Okay, so our first one is, let's see what color did I make that? Blue. So step 1, okay, so if you look, that is the blue segment. Okay, so for this part, we are going to need the specific heat of ice. So we'll call C ice is equal to 2.03 joules per gram degree Celsius. And that is our specific heat of ice. Okay, so one more thing we need to do before we kind of go through this. So this is with, we'll call it 1 mole of water. 1 mole of water is 18 grams of water. Okay, which is important. This, and this mass, this, and this moles. Okay, so we have our mass and we have our moles. Okay, so that's our C for ice. Okay, so our Q is going to equal MC delta T. So our mass, 18 grams times 2.03 joules per gram degree Celsius. Okay, so if we look at this segment, it's starting at negative 25. This segment stops at the freezing temperature of our substance. So since this is water, it's 0. This would have been ethanol or something other than water. Again, you're looking for that freezing temperature. That's where this segment stops. Okay, so we're going to have, let's see, our temperature final, which is 0, subtract negative 25 degrees Celsius. Okay, so if we solve this here, we get that Q for this step was 913.5 joules, which is 0.914 kilojoules. And so I'm going to solve this in kilojoules because these here are in kilojoules as well. Okay, so that was first. So our next segment, we're looking at the energy now to break the interactions of solid water to turn it into a liquid. That's our orange there. So for this step here, we need the enthalpy of fusion for water, and that is 6.01 kilojoules per mole. Okay, so this is segment 2. Okay, so Q equals, up here, N times the enthalpy of fusion. So in the problem, we have 1 mole of water. So 1 mole times 6.01 kilojoules per mole. That cancels, we get 6.01 kilojoules of energy for that segment. Okay, so 1 and 2. 3 is our standard Q equals MC delta T. Okay, but for now, liquid water. So that one was yellow. 3. Okay, so for this one, sea water is the standard 4.184 joules per gram degree Celsius. Okay. Q equals M, which was our 18, times 4.184 joules per gram degree Celsius. Okay, multiplied by our delta T. Let's go up and look. So it's this, our water is in the liquid phase from 0 to 100. So that's going to be our initial and final. Our boiling temperature is our final. Our freezing temperature is our initial. Okay, so again, this is water. We know that's 0 and 100. But again, if this gave you something else like ethanol, we're going between the freezing and boiling temperatures when it is in the liquid phase. Okay, so this will be 100 minus 0. Okay, so MC delta T, I got 7,531.2 joules, which is 7.5, we'll call it 31 kilojoules. Okay, so next we've gone 1, 2, 3. We're on the pink segment now. So we're looking at vaporization. So number 4 here, we need delta H of vaporization. They're color coded there. It's pink. Okay, so we go back and look at all of those segments there. That one is pink. Okay, so for water, the enthalpy of vaporization is 40.67 kilojoules per mole. So that is actually quite large. And that is because water has those really strong hydrogen bonds. So that's quite large. If you were to look something like ethanol up or benzene or something like that, this enthalpy of vaporization would be much, much lower. Again, this has to do with separating out those molecules, and the stronger they interact, like through hydrogen bonding or dipole-dipole, the more energy it takes to do that. So that's why this is so large. So this is by far going to be our largest energy contribution to our heat or energy diagram above. Okay, so we just have the 1 mole. So Q equals the 1 mole times 40.67 kilojoules per mole gives us 40.67 kilojoules of energy. So again, 0.9, 6, 7, 40. So it takes a whole lot of energy for water to separate those water molecules. Okay, so 5, the last step. Now that we're in the gas phase, we're just heating up the gas in that last segment. Okay, so we need C for the gas phase, or steam. Okay, so C for our steam is 1.84 kilojoules per mole. Okay, so Q is equal to M, or 18, times 1.84 kilo, I'm sorry, joules per mole Kelvin. Joules per mole Kelvin. Sorry, I got my units mixed up there. Specific heat in joules per mole Kelvin. Okay, so 18 times our 1.84, and now looking at the temperature. So this is 100, and now we're heating up the gas to 125. So we're going from 100 to about 125, so right here on this segment. So final 125 minus initial at 100. Okay, so, 18 times 1.84 times 25, a whopping 828 joules, which gives us 0.828 kilojoules. Okay, so let's go back and look. So this one was segment 5. That's our energy for that segment. Okay. So that's our energy for that segment. Energy for that segment. Energy for that segment there. And then finally, the last one, our energy for that segment there. Okay, so I can barely get them all on here. I think I can quite. Okay, so to find the amount of energy to go from, again, our negative 25 to our 125 for a mole of water or 18 grams, to find that total energy, we're going to add up the energy from each segment. So our 0.914 plus 6.01 plus 7.531 plus 40.67 plus 0.828. Okay, so if we sum all of those together, we get 56.0 kilojoules. So all of those together, again, added up, all of our 5 steps, 1, 2, 3, 4, 5, sum those steps together, 56 kilojoules worth of energy to take 1 mole of water from negative 25 degrees Celsius in the solid phase all the way up to 125 degrees Celsius in the gas phase. Okay, so again, most of this energy comes from this step here because of those extremely strong interactions between those water molecules. It does take a lot of energy to overcome those hydrogen bonds to turn liquid water into water in the gas phase. Okay, so having sort of said that, let's take a look at what we call a phase diagram. Okay, so a phase diagram, I'm going to come up just a little so we can get this whole picture in. So a phase diagram, actually before we kind of do this, kind of wanted to back off. I'm going to go really kind of backed off so you can kind of get most of the picture here. So again, we had those 5 steps all kind of color-coded there. And we calculated each one of those 5 steps differently with, again, our sort of more vertical regions using Q equals MC delta T, and our flatter regions using enthalpy of vaporization and enthalpy of fusion. Okay, so back to this. This is what we call a phase diagram. So the phase that a particular substance is in is dependent on the temperature and the pressure. Okay, so temperature and pressure. So this looks like it could be carbon dioxide, if I'm not mistaken. Doesn't matter, they all have something that looks similar to this. Most things have this sort of Y-looking shape. Some other things are a little bit more interesting, like helium, for example. Very interesting, that one. But for the most part, we get something like this. Okay, so at very low temperatures and higher pressures, we get the solid phase. Okay, at high temperatures and low pressures, we get gas phase. And in sort of intermediate temperatures and pressures, we get the liquid phase. So all of these lines here represent equilibrium. So if you are at a point, say on this line right here, your substance gas and liquid phase would be in equilibrium. So you'd have both liquid and gas occurring simultaneously in your sample. So this one here, on that line, you would have your solid and liquid phases together coexisting in phase. Here, solid and gas. And then right here, where all of those segments meet, that's called the triple point. You can probably guess that's a special point where your solid, your liquid, and your gas are in equilibrium. So you can have all 3 of your phases coexisting simultaneously at that particular temperature and pressure. Okay, so as you cross through going from phase to phase, we get different names or terms that kind of go with these. A lot of them you've heard of before. So say going from a solid to a liquid is called melting. Going from liquid to solid is freezing. Going from liquid to gas is vaporization. Going from gas to liquid is condensation. Maybe more exotic down here, going from solid to gas is sublimation, which we saw in one of the labs, one of the early labs. Our ammonium chloride went from, at our normal temperatures and pressures, went from solid to gas. And then the opposite way, going from gas to solid, that's called deposition. Okay, so here's again a phase diagram with the major points. Okay, so one I didn't talk about, one that's kind of unique, is the critical point. So you see up here, we kind of have this one keeps going on off the page. This one ends at a point. A critical point is the pressure and temperature about which you don't have a distinct liquid and gas phase. So you get what's called a supercritical fluid up here. It has both gas and liquid-like properties. It flows kind of like a liquid, but it can sort of travel through substances like a gas and has a lot of really interesting intermediate properties there. So it's sort of used as a gas, or excuse me, a liquid almost in its solvent abilities, but it's able to, say, extract, to get into like, to really sort of pull things out of substances a lot better than a normal solvent would be. So for example, one of the supercritical fluids used quite often is carbon dioxide. So it's used to extract caffeine from coffee beans to give you the decaffeinated version. Before supercritical fluids, we'd have to use solvents to do that. So smelly, stinky organic compounds that we would then have to remove after the extraction process. So they do have a lot of fantastic properties, supercritical fluids. So we're not going to see a whole lot of them in this class because they do exist at such high temperatures and pressures. Okay, but here is, like I said, a nice phase diagram. Okay, so we're going to look at two different phase diagrams. Okay, so we have CO2. So we have CO2 above. So again, very similar to the one that I saw there. But now we have a scale on here. So we can kind of see where a lot of these points lie. So first, a lot of times we refer to a normal pressure. A normal pressure is 1 atmosphere of pressure. So if you're doing some of the problems in the book, practicing homework, things like that, and it says what phase would something be at 31 degrees Celsius and at normal pressure. So normal pressure means 1 atmosphere. So if we look for CO2, our normal pressure at 31 degrees Celsius would put us here in the gas phase. So normal sort of sunny day for CO2, normal atmospheric pressure, and, you know, nice hot sunny day would be solidly here in the gas phase. Okay, so the triple point for CO2, 5 atmospheres and negative 56.7. The liquid phase for CO2 only exists at pressures above 5 atmospheres. So if you've ever sort of used this for Halloween or practical purposes, you can buy what's called dry ice, which is CO2 in the solid form. So you can buy this at grocery stores for the most part. So to go from gas to solid, you just have to sort of decrease the pressure at normal atmospheres. So at the normal atmosphere, to go from gas to solid, you just have to decrease it to negative 78.5. To go into the liquid phase, we would have to bump up the pressure quite a bit. So we can buy carbon dioxide in the solid phase. It's really difficult to get into the liquid phase because of those super high pressures that are needed. Okay, so for example, in this problem, they want to know what phase we would expect to find CO2 at 70 atmospheres of pressure and negative 78.5 degrees Celsius. Okay, so we look, it's just like using any other graph. We find 70, and then we're going to find our negative 78.5. So negative 78.5 to roughly 70 puts us right here, squarely in the solid phase. So under these conditions, CO2 would definitely be a solid. So this one, 6 atmospheres of pressure and 30 degrees Celsius. So same thing, just slightly above 5. And to our temperature of slightly less than 31, we would get that CO2 would be in the gas phase. Okay, so we can do one more. Let's say, what phase would we expect CO2 to be in at, we'll go 60 atmospheres of pressure and 0 degrees Celsius. Okay, so 60 probably somewhere, up here. Let's see, this is negative, positive, 0, somewhere here. So we'll take 0 up to get into probably somewhere in the 60s. I'm guessing this dot is somewhere over here. So here we would expect this one to be in the, say, liquid phase. Okay, so also with these, you can also have them be read at what temperature? So one more. Is CO2 solid in equilibrium with CO2 liquid at, we'll call it at 72.9 atmospheres. And so other questions you might get with a phase diagram is to know at what temperature you'd expect CO2 solid and liquid to be in equilibrium at a particular pressure. So again, what it means to be in equilibrium, so that's equilibrium, sorry. Which again means they coexist together, is you need to be on one of these lines. So if we look for solid and liquid, we're looking at this line right here. Okay, so our 72.9, to fall on that line, our temperature would need to be that negative 56.7. Okay, so those are the types of questions that you would be expected to answer with a phase diagram. Okay, so let's look at now a phase diagram for water. So again, similar things, just the shape is similar. This one is more up and down. This one is more sort of sloped this way. But for the most part, kind of that Y shape. Triple point at much, much more accessible pressures and temperatures for water. The normal sort of here, you can, at normal pressures, so again, our 1 atmosphere, very easily you can access the solid, liquid, and gas phases quite easily. That's one of the sort of unique properties of water. At normal pressures, you can easily go, again, remember this is the solid phase, liquid, and gas. And up here we have such a tiny little area for the liquid phase. For water, thank goodness, it's gigantic, which is why we have so much liquid water on the earth. Okay, but with this diagram, we can do the same things. At a pressure of 4 atmospheres and a temperature of negative 20, what would we expect phase to find water in? Okay, so somewhere over here, 4 and our negative 20. Okay, so somewhere here, definitely squarely in the solid phase. Next one, pressure of 100, so maybe say halfway between those, and temperature of 120, which was right here. So this one here looks to be in the liquid phase. So again, we're reading this the same way that we did up here. You just use your X and Y coordinates and figure out which phase it's going to be in. Again, our solids are the low temperatures, high pressures, liquids, intermediate, gases, high temperatures, low pressures. Okay, so things that hopefully look familiar at the normal pressure, We cross the line here, not surprisingly, at 0. And at normal temperatures, we cross the line at 100. So our freezing and our boiling, we're at, again, our pressure, which is 1 atmosphere, where it crosses that line that separates solid and liquid. Okay, so same thing here, where it crosses liquid and gas, we get our boiling temperature. So those are called the normal freezing points and normal boiling points. So for water, the triple point is just above 0 and with a very, very low pressure of 0.006 atmospheres. Okay, so pretty low pressure and temperature to access the triple point. So critical point of water, about 373 degrees Celsius with a pressure of 217. So quite high, the pressure and temperature we need to get the supercritical fluid state of water. Okay, so this is pretty much it for chapter 11. So being able to look at and read a phase diagram, again, being able to identify which particular phase you would be in at a pressure and temperature. Also, again, recognizing that freezing point and boiling points do change with pressure. Like, for example, if we were to go up to 100, atmospheres of pressure, our freezing point right here would be much lower, and our boiling point over here would be much higher. Okay, so if we increase the pressure, we'd freeze at a lower temperature. If we increase that pressure, we would boil at a higher temperature. So the temperature at which a substance freezes and boils, of course, depends on the temperature, but it also depends on the pressure. So again, we see that here, where again, we can change the freezing and boiling temperature of a substance by changing the pressure. And that's why I think pressure cookers are so popular right now. You can increase the pressure and therefore increase the boiling temperature. So you can look at the shape of this curve. If you pressurize something, again, even just say doubling it to 2 atmospheres, instead of boiling at 100, it's now crossing this line a little bit further off. You are increasing the temperature at which something will boil. So it's getting hotter, so you can cook your food a little bit faster in a pressure cooker. Okay, so that is the end of phase diagrams, and this concludes the material you need for chapter 11.